Hi, in this video we're going to look at the chain rule for vector valued functions. So what do I mean by this? So let's say that you have a vector x in Rn, and I apply a vector valued function g to x. So by vector valued function, I mean that g takes as input a vector, here x in Rn, and it also outputs a vector, let's say a vector in Rk, and then I apply another function to this, say f, and f is also vector valued, so f takes as input Rk, and it outputs, say, Rm. And then let's call the output y. So essentially, our input is in Rn, we apply the functions g and f, and the output is a y, which is a vector in Rm. And we're going to look at the derivative of this vector y with respect to the vector x. Now, what do I mean by the derivative of y, which is a vector, with respect to the vector x? So what I mean here is the generalization of the derivative to vector valued functions, and that's this Jacobian matrix. I'll talk about the Jacobian matrix a bit more in a bit, but basically it's a matrix consisting of the partial derivatives of each of the component functions in y. Anyways, what the chain rule says is that this is equal to the derivative of f with respect to g. So this is, again, a Jacobian matrix, times the derivative of g with respect to x, which is, again, a Jacobian matrix. So I want to point out here that this looks exactly the same as the chain rule for scalar valued functions, except now we have these Jacobian matrices here. And instead of multiplying them, we take the matrix product. Okay, so let's talk a bit more about this Jacobian matrix. So since y is a vector with m components, I'm going to write it out like this. So y is going to consist of each of the individual component functions. So y1 of x, y2 of x, and so on. Where each of these yi's are a function from Rn to R. And what the Jacobian matrix is it's a matrix consisting of the various partial derivatives of x with respect to each of these component functions. So, for example, let's take the partial of y1 with respect to the first component of x1, like so. And we're going to put that as an entry in our matrix. And in the next column, we're going to take the partial of y1 with respect to x2. So with respect to the second x component, and so on. And the last entry here will be the partial of y1 with respect to xn, right? Because X has n components. So that makes up one row of our Jacobian matrix. And in the next row, we're going to do exactly the same thing with y2. So we're going to put partial of y2 with respect to x1, partial of y2 with respect to x2, and so on. So partial of y2 with respect to xn. So we'll keep doing this, and our last row in the matrix will be the partial of ym with respect to each of the components of x. Like so. So this is the definition of the Jacobian matrix. So this is what I mean here when I write partial of y with respect to x. This is a matrix like this. And that's also what I mean here. So this is the Jacobian of f with respect to g. And this is also the Jacobian of g with respect to x. Okay, so let's have a look at the proof of the chain rule. So first of all, let me just copy over the definition of the Jacobian. Okay, now what I'm going to do is I'm going to analyze one of the entries in this matrix, say the first one here. So let's look at the partial of y1 with respect to x1. So first, let me remind you that y is f of g of x. So in particular, when we're taking the partial of y1 with respect to x1, what we're really saying is we're taking the partial of this function f, or the first component of f, with respect to x1. Now this function f1 takes in a vector value as input, so it takes in g as input. So each of these component functions take in rk as input, and the output space is a real number. So if we want to compute this quantity here, since this f1 takes a vector as input, we have to use the multivariate chain rule. So what we want to do is sum over all of the component functions of g. So say I equals 1 up to k of the partial of f1 with respect to each of the component functions of g. So gi times the partial of gi with respect to x1. So this is by the multivariate chain rule. So I can rewrite this component of the matrix as this value. So let me do that. So this component of the matrix, I'm going to write like this. And now if you go through and try to compute one of these other partial derivatives, let's say this one, the computations are going to be the same, except instead of this x1, you replace with the x2, right? And if you're computing the partial of a different component function, say y2, then what you do is you replace, instead of f1, you replace that with a corresponding number, right? Everything else is the same. So what this means is that if we write out what that looks like, it's going to look something like this. So for the last column in the first row, we'll have this. So we're still looking at the first component function of f. But now with respect to the last component of x, so xn. And down here, we have fm with respect to x1. And here we have fm with respect to xn. Now, what you'll notice is that in each of the components of this matrix, we have this sum of products. And so we might be able to simplify this whole expression as a product of two different matrices. So what I'm going to try to do is exactly that. So it might make sense that that these terms here form the rows of our matrix, of the first matrix, and these terms form the columns of the second matrix. And then when we multiply these two matrices in green and blue, hopefully that gives us the corresponding term in this matrix. So let me go about doing that. Okay, so for our green matrix, we want its rows to be terms like this. So partial of f1 with respect to all of the gi's. So what I'm going to do is I'm going to unpack that across the row here. Okay, so this first row is the partial of f1 with respect to all of the components of G. And for the next row, it's going to be the partials of F2 with respect to G, and so on. So the last row is going to be partial of Fm with respect to G. Like that. And let me move this over a bit. So I have space for the blue matrix. So for the blue matrix, we said that we wanted these terms to be the columns of the matrix. So let's try and do that. So I'm going to make this term the columns of the matrix. So I'm going to unpack all of the GIs. So it's going to look like G1 with respect to X1, partial of G2 with respect to X1, and so on, up to the partial of GK with respect to X1. The next column would be all of the partials with respect to X2. And then in the last column we have the partials of G with respect to the last component of X, which is Xn. Like that. Now, let's just make sure that, at least for the first component of this matrix, we get the correct value by multiplying these two matrices out, as I hinted about earlier. So this first component of our matrix, sorry, the first row and first column, we want looking something like this. So I'll just copy that down here. And let's have a look at what happens when we multiply the first row and first column. Well, if you multiply this out using the standard matrix product, what you'll see is that, well, these two terms get multiplied together. Then the next two get multiplied together, and so on. And then these last terms get multiplied together. And all of those terms are added together. And that's exactly what we have here. And if you go through the other entries in the matrix, you'll see that we actually do get exactly what we want. So let me formalize that a bit more. Now let me give these two matrices some names. So I'll call this partial F with respect to partial G and partial G with respect to partial X. Now I've given these names that suggest these are the Jacobian matrices, and indeed they are. So for this green matrix, we can check that, well, each row of the matrix corresponds to one particular Fi, and the components in each row are the partials with respect to each of the components in G. Similarly, for the blue matrix here, we see that each row corresponds to a particular component of G, and the elements in that row are the partials with respect to each of the components of X. Now, as I said, I'll show a bit more formally that that when you multiply out these two matrices, we do indeed get the correct expression. So let's go back to this matrix here. Let me give it a better name, say J. And I'm going to look at an arbitrary element of this matrix, say with index A, comma B. So what is that? So J, A, comma B. Okay, so it's the 8th row. And the 8th row means that we're looking at a component, a function fa. And with respect to xb. And this we can write as so if I make this this a row vector and this a column vector, we get this. Times a column vector. That looks like that. And if we go back to our diagram here, notice that this is exactly the 8th row of this matrix here. And this value here is exactly the bth column of this matrix. So that concludes our proof. So to summarize, what we've showed is if you have y equals g of f of x, where all of these are vectors, then the derivative of y with respect to x, which is really the Jacobian matrix, can be written as a product of two separate Jacobian matrices. So the Jacobian of G with respect to F times, or matrix product, the Jacobian of F with respect to X. And this is a generalization of the chain rule for scalar valued functions.